Okay, so I'll start today's session. Welcome to session 8 of problem solving for the course Regression Analysis. I am the TA Shreya, and today I'll be solving problems pertaining to week 8 lectures. And before diving into that, I would like to review some of the concepts, the related concepts that were discussed in the previous week, that is week 7. So let's start. Okay, so in week 7 we learned the model accuracy checking parameters and how what are the assumptions that we usually follow. These three assumptions on expectations of the errors: the variance should be constant, and the epsilon i's, that is the errors, are independently distributed and identical random variables following a normal distribution with mean 0 and variance sigma square. So these are the assumptions on the errors. By and keeping these assumptions in mind, we have devised the least square estimates, and we wanted to check if the assumptions they do hold true. And also we also learned about leverage point. That was an unusual observation in X, that is the predictor or the regressor. And we also learned about influential observations, which influence the regression line and change from the change the trend of the regression line. For example, if this is a line and this is X, this is Y, then some point here the usual range of X is here. This is something unusual, but it is falling along the same regression line. So such a point is a leverage point. Whereas if we have something which is altering, let's say this is our usual original line, and we have some observation X in the extreme right, and here we have this observation, then the new regression line becomes this one. So the trend is getting altered. So such a point is an influential point. Okay, so these things we learned. Also we learned about the hat matrix and the diagonals, what they signify. They signify the deviation of the X observations from their mean, from the mean X observations. And this was the formula, and this matrix actually transforms y to y cap, and that is why y hat, and that is why it's called a hat matrix. And we also learned some properties of hat matrix, that is, it is a symmetric matrix, H transpose equal to H, and it's an idempotent, that is H square equal to H. Similarly, we learned about types of residuals. There could be the normal residuals, that is the EIs, and there could be standardized residuals, which is denoted by DI. Please make sure that you note the notations by which each of the residuals are denoted, because sometimes in questions you might get some questions which have some other, if it is not mentioned otherwise, then these three are the standard notations that will be followed. So please note that EI will, unless mentioned otherwise, it will mean the normal residuals, and DIs would mean the standardized residuals, that is nothing but EI by square root of the MS residual, which is an estimate of the sigma square. And if we just divide by the DI values by root over 1 minus HII, then we would get the studentized residuals. And the advantage is the variance of studentized residuals would be 1, and these derivations were done in class. And also we learned something about the press residual, which is the residual computed by uh, I mean calculating the difference from the observed variable for the observed variable or response for the ith individual, divide minus the predicted response when we are leaving out the ith observation. So we discussed these, and also we learnt about some plots and how we can check the model accuracy assumptions that we had taken earlier, like the residual versus fitted. There should be a non-random pattern, and we should have a band which should be near to 0, and there should not be any open funnel or closed funnel, because those are situations that we do not want. We want the variances to be equal. So, and then residual versus fit and residual versus regressors, are they equivalent? Well, yes, in case of simple linear regression, but no when it's a multiple linear regression. So also we learned about how to get a residual plot, and the slope would always be beta j. Okay, and if there's less scatter, then it would imply that there is a stronger relationship. And also we learned about the normal probability plot. We are plotting the cumulative probabilities and the residuals, and if they fall in a straight line, then we would conclude that the residuals are normally distributed. So in order to test this assumption, we plot the normality probability plots, and then we jumped on to week 8 lectures. Now, whatever I have mentioned that so far was discussed in week 7. Now, in this week, we have lectures which say how we will test if an observation is an influential or a leverage point. Now, previously whatever we have learned, that is the intuition behind it. Here in this week we have the analytical thresholds have been provided for each of the following methods. And also we learned it was discussed this week, even though this pertains to last week things, that what is the press statistic. So as I said earlier, the residual leaving out the ith observation is calculated as the here I have written it. Where is it? Yi minus yi hat prime. So this was yi minus y leaving out I hat. This thing is the ith residual, and the press statistic is nothing but summation I equal to 1 to n. Let's assume there are n observations, ei square, which is equal, this ei can also be equivalently written as ei by 1 minus hii. So this one is nothing but ei square by 1 minus hii square, I equal to 1 to n. So this is how the press statistic is computed, and if the press statistic is greater than the SS residual, then we say that the model is not well fit. Okay, so we'll also review each of the following tests in this order. So the first thing that we learned was how to test for an influential observation or a leverage point using the hat matrix. Okay, so the hat matrix, as we all know, we have a model y equal to x beta plus epsilon. Okay, so the hat matrix is calculated as x into x transpose x inverse x transpose, and the ith diagonal element can be written as xi transpose x transpose x inverse xi, and we have already learned what it measures, the distance. 1 second. Okay. Hello, good evening.
Good evening, ma'am.
Good evening. So I have started it. I am just through it. So if you please let me know if you can see my screen. Can you see it?
Yes, ma'am, I can see.
Okay, I've just started. I'm just giving a recap of week 8 lectures. So, do you have any doubts so far?
No, ma'am. So I have doubt in the examination, ma'am.
Okay.
So in exam, so if the problem, if they ask the matrix related problem, means how we can solve, ma'am.
The see, during exams, I think it will be a 3-hour exam. So the problems will be given accordingly. I mean, you won't have two large matrices to, uh, I
Yes,
mean,
ma'am.
so the calculation won't be as rigorous as possible, but try to practice. And I mean, these problems will, I mean, I hope it will be given in such a way that it's manageable, and just try to practice more and solve more so that you can do, calculations faster.
Okay.
Okay.
Thank you.
Any other doubt related to the subjects or lectures
No,
or
ma'am.
the
No, ma'am.
tutorial sessions? Okay. And did you follow week 8 lectures?
So I watched only one video, ma'am.
Okay, the first one?
Yes, ma'am.
Okay, fine. Then I think you'll be able to follow. Okay, so I just started with, I'll just recapitulate what I was telling. So before
Okay.
that, I just described what we had learned during week 7 and
Okay.
how it is continued in week 8 lectures. So please go back and check week 7 slides, or the recording of this one will also be available. So I'll just start from here once again. So in this week, what we were learning was, we learned how to test for influential and leverage point observations, the first lecture that you have attended. So influential observations are those which change the trend of the regression line, and or they change the entire regression line, and leverage point is some unusual observation in x which might or might not, if it's a strictly a leverage point, then it will not change the regression line, like it will follow the regression trend. So this was the intuition, and we had learned that the hat matrix, the ith diagonal element of the hat matrix, this one gives a measure of the distance of ith x from mean x values. So using these two intuitions, now we will it was some analytical threshold was provided during this week, so I was just discussing that. So since HII measures the distance of the ith x from mean x, then mean h is given as summation HII. See, there will be I equal to 1 to n observations. Okay, so this thing. Now H matrix is this one. Okay, so summation HII, that is sum of the diagonal elements, is and the average. So the numerator part is nothing but the trace of H matrix by n. And now since H is a full rank matrix, so trace of H is rank of H by n, and rank of H is nothing but the total number of parameters that we are taking. So here, including beta naught and k minus 1, beta 1 to beta k minus 1, we have in total k parameters, let's say. So this would be then k by n. And the criteria to detect a leverage point is that if the ith observation has an HII value of greater than 2k by n, then we say it's a leverage point. Okay, so another criteria that was used was the Cook's D statistic. So the Cook statistic was something like di yi cap minus y cap prime yi cap minus y cap divided by k into ms residuals, where yi cap was nothing but the predicted y leaving out ith observation. That is, if let's say 1 2 3 4 5, then y5 hat would be, if I just remove this one from the set, and with these observation I'll fit the regression and get the fitted values at, so x will also be x1 x2 x5, so fitted value at x5, that will be my y5 cap. Okay, so this one, it gives actually the squared distance between yi cap and y hat. So if the difference is large, then it means that the ith observation is an influential point, because the presence of I and the absence of I is making a huge difference in the predicted y. That is, that depends on the regression line. So that is why if the square distance is large, then we can say that the ith observation is an influential point. Now how large it is, we can give a subjective threshold, that if di are any di is larger than the others. Okay, so this one was there. And also we learnt about df fits. So df fit I was also similarly given as yi hat minus yi hat. It's not the square distance but just the distance, and it is scaled by ms residuals I into hii, where ms residual I is the same thing. We leave out the ith observation. These are the steps. Leave out the ith observation, fit regression with the remaining, and from this model we compute ms residuals. Okay, and if the df fit for ith observation is greater than this threshold 2 root k by 9, then we say that the ith observation is possibly an influential observation. Okay, and so this df fit is calculated for each I, and similarly we have df beta. Now df beta, actually it measures how much the jth beta changes if ith observation is removed. So df beta I j, that is this j stands for the beta j and I stands for the observation. Okay, so how is beta j changing? So if we consider a multiple linear regression, so let's say we have something like this. Okay, y equal to beta naught plus beta 1 x1 plus beta 2 x2. So if I say that df beta I3, I2, what I mean is that how is beta 2 changing if the ith observation is removed. Similarly, we can calculate how these estimates change if the ith observation is removed. Okay, so for df beta we compute ij combinations to test which observation is affecting which one, and the formula is similarly given by beta ji by root over ms residual, leaving out the ith observation, and x prime x inverse, the jth element. Okay, this one comes from the variance of beta hat. So similarly, variance of beta hat was something sigma square x transpose x inverse, and the diagonal element would give the variance of that particular beta. So since we are here, we are concerned about some jth variable beta, let's say beta 2 is here, then we would have the 2th element of x transpose x inverse. Okay, and the criteria was df beta ij, if it is greater than 2 by root n, then we say that the ith observation is an influential observation. Okay, so the first lecture for week 8 entails to these 4 techniques of assessing which is a possible influential observation. And also the second lecture that you will see, it pertains to transformations to tackle model inadequacy. So what was that? We had assumed that this would be sigma square, and it would be a constant thing. It like there would be no increase or decrease in the variance as the observations, the predictors increase or decrease. So those kind of situations were not assumed when we first derived our least square estimates. So these were the assumptions that the variance is the variance is constant. This we had assumed. Now if there is deviation from these assumptions, like the variance is non-constant or it is some function of the expectation, then we have to perform some transformations so that our results are not grossly deviating. So for this we had applied some transformation, and you will see it would, if sigma square is proportional to something mu to the power a, then we would write it as g mu, right? Since this would be the function with which sigma square and mu are related, then we would have something as log y if a equal to 2, and if a not equals to 2, we would have this as 1 minus pi by, okay, I'll get back to this. Okay, I'm sorry, I forgot the exact thing. It would be y to the power 1 minus a by 2. So based on the relationship between sigma square and mu, these are some possible transformations which if we make, then the variance would be stabilized and it would not vary with the expectation or with anything else. So these were the variance stabilizing transformations that we could perform. And also we learned about a second class of transformation that would linearize our variables. Like for example, if we have something like y equal to beta naught e to the power beta 1x, then if we take log y, we would have something like log beta naught plus beta 1x. So this one we can write it as some beta naught star, and then this can be written as some y star. Then this transformation will again make the the equation a linear equation, linear in parameters. Okay, so these transformations also we learned in the second lecture of week 8. So today the problems that I have, they pertain to the first lecture, so I hope it won't be a problem for you to follow. Okay, and the next week we'll discuss problems on the second from transformation onwards. Okay, so shall I start the
Yes,
problems? Okay.
ma'am, actually my battery is low, ma'am.
Okay.
It's a 13% only. I need to charge my phone.
Okay.
I don't know how can I follow.
Can't you plug it in and see?
So actually here the power cut, ma'am.
Okay. Okay, so
So
if you are facing too much of an issue, anyway this session is getting recorded. So
okay, ma'am.
if you have issues in continuing, then you
Yes.
can log out now and can see the lectures.
Okay, ma'am. Thank you, ma'am. Sorry for the inconvenience, ma'am.
No, it's fine.
Okay.
Okay. Okay. So as I was saying, the HII is a measure of the distance. So in this case, it would measure the mean of y values, the distance between x value from the mean of x values for all observations. Okay, so this was discussed. in lectures. Okay, so we'll move on to the second one. So what does a normal probability plot help you to test? So this also I explained, or so as you can see, the normal probability plots, they are plotting the residuals and the cumulative probabilities. So if the residuals are from some normal distribution, then these will fall in the same line. So if you have heard of quantile plots, it's that. So we are just taking the sample observations and plotting it in increasing order versus the expected probability distribution. So that would give us the a way to assess the normality of the residuals. Okay, because here we are plotting the residuals in increasing order, and here we are giving the cumulative probability. Okay, and if they fall along the same line, then we would say that the residuals follow a normal distribution. Okay, so we'll move on to the next one. So here we have been given a table where each of the diagonal elements of the hat matrix, while fitting this model with three unknown parameters beta naught, beta 1, beta 2, has been given, and there are 20 observations. So the sample size here is 20. Number of parameters to be estimated, unknown parameters, that is k, is 1, 2 and 3. So we have been asked, is observation 3 an outlying observation in terms of its x value? So we have to assess using this HII value that we have. If it is an outlying observation in terms of its x, it means whether it's a leverage point or not. So in order to calculate if it's a leverage point or not, what we have to do is that we have to compute h bar. So h bar, we can do one thing, we can just take a sum from here and get h bar the average, or since we have this value that we have already derived, we'll directly substitute k and n values over here. So we would have 3 by 20. So it would be 0.15. And what was our criteria? Our criteria was ith observation is a leverage point if HII is greater than 2k by n. So here HII is 0.372 and 2k by n is 2 into 0.15, that is 0.3. So here we see that this observation is greater than 0.3 So we say that yes, the third observation is a leverage point. Okay, so the answer is A. So similarly, here they are asking if the 15th observation is an outlying observation. So same thing, h bar equal to k by n, that is 3 by 20 equal to 0.15, and h15 is which one? This one. Which is greater than 0.3, that is 2k by n. So 15th observation is a leverage. Okay. So we'll quickly move on to the next one. So here we have been asked to consider the problem in the data in problem 3. So same thing. Okay. So here we have the same data for 20 data points. Just a second. Okay. So here we have 20 data points, and in order to identify possible influential observations, the total number of DF fits that needs to be computed. So DF fit was nothing, but it was yi minus, it was difference between this fit and this one. Divided by root over ms residual into HII, if I'm not wrong. ms residual ith residual. So please pardon me, I'll just write it afresh. So it was ms residual leaving out the ith observation into HII. So we had to calculate the DF fit for each of the ith observation. So DF fit for this one, DF fit for this one, and similarly DF fit for this one. So here the total number of DF fits to be computed is 20. Okay. But if the same question is repeated for DF betas, then how should we do it? So if I was giving this example, so df beta for the jth variable for beta 2 would measure how the ith observation is changing beta 2. So similarly, the ith observation could change beta 1 and beta naught as well. So you remember we were writing df beta ij. So total there would be ij combinations and ij df betas. So I was telling the jth one, let's say it corresponds to the unknown parameters, and I corresponds to the number of sample ID. Okay, so then here I ranges from 1 to 20 and j ranges from 1 to 3. J ranges from 1 to 3. So total number of j's are 3, total number of i's are 20. So the total number of df betas would be 3 into 20, that is 60. Okay, I hope this is clear. Then let's move on to this question. Okay, so the problem remains the same, and Cook's distance, they have given a formula. So it can be shown, I'm not going into the details of this, that the Cook's distance that we were writing by some problem I'm doing. This thing can be equivalently written as ri square by k hii by 1 minus hii. Now one thing we have to note here is that this is the ri is, if nothing else is mentioned, we will consider it as, we have to, this is nothing but the studentized residuals. Okay, so Ri is nothing but Ei by root over ms residual into 1 minus hii. Okay, so why I am telling this is that here the expression is given in terms of Ri, but in the data we have been given the Ei, that is the normal residuals. So if we base our calculations, if we just put Ei values in R, then we would get totally wrong answers. That is the reason we should always be careful. If it is not mentioned what Ri means, then we would always assume Ri to be a studentized residual. Okay, sorry. So this thing can be then written as Ei square by k ms residual 1 minus hii into hii by 1 minus hii. So here we would have a square and he would have some hii. Okay, so we'll just compute, just a second. Okay, so here we have been asked to find D13. So our D13, I mean our E13 is this one. So it will be 3.947 whole square into HII is this one, 0.109 by the same thing. K is 3. MS residual. MS residual will be SS residuals by N minus K and into 1 minus 0.109 whole square. So SS residual will be nothing but summation EI square. So here we have EI, we would compute EI square and then we would take a summation of EI square. It would come out as 109.9. Okay, so this will be 109.9. Okay, let me do it in a fresh page. So as I was saying, this is nothing but di equal to ri square by k, hii by 1 minus hii is nothing but ei square into hii by k ms residual 1 minus hii whole square. Okay, so we were computing this thing for 13. So here we would have something like minus 3.947 whole square into 0.109 by k is 3. This is SS residual by n minus k. This is 1 minus 0.109 whole square. So I was telling how to SS residual is nothing but sum of summation EI square. This one, sorry, we would have something here and it came out to be 109 point, just a second, 109.95. okay, and here n we have equal to 20. So and k we have 3 normal equations, so k will be 3 unknown parameters, and df for this thing is n minus k equal to 17. So we would have this as minus 3.947 whole square to 0.109 by 3 into this thing is something, it came out as 6.47. so this will be 6.47 to 1 minus 0.109 whole square. Okay, and if we calculate the value, we'll get something like 0.11. Okay, please check this one for some calculation error, but this is how the technique should be performed. Okay, just be careful if we have EI or RI or DI over here. If it's DI, then it will change accordingly. Okay, fine. So the next one is this one. So if press is substantially larger than SS residual, it indicates that the fitted model is not likely to predict new observation well, because press would give summation EI square, and if EI is greater than greater than the normal residual, so this is residual leaving out ith observation, and this is residual ith residual from usual model. So our target, if you remember, for least square error, the target was to minimize the residual sum of squares. So if we are unable to do that, then this thing will be large than EI, like leaving out the ith observation is causing a lot of difference in the residuals. So then we can say that if this holds, that press is substantially larger than sum of squares due to residuals, then we'll say that the fitted model is not likely to predict new observations well, because the ith observation, if I is an influential observation, if there are more influential observation, then the press statistic would be higher. So this case arises if I is a ith observation is an influential observation. So if there are more influential observations here, then automatically the press statistic would become higher than because it's a squared term. Okay, so if this is greater than this one, its square will also be greater than this one. So if there are more influential observations, then as a consequence the press statistic would also be greater, and then the fitted model that we have is not likely to predict new observation well, because the fitted model, this one with all observation, that is not following the usual trend. It's getting somewhere deviated, like this or like this. It should be like this, but due to the presence of more and more influential observation, it is getting deviated. So it will not fit the general pattern and is not likely to predict new observation. Okay, so this was all about today's session. I have explained mostly problems based on the first lecture. So in the next class we'll discuss problems related to the transformations that I have discussed today, and the upcoming the transformations that will be discussed during the lectures of the upcoming week. So stay tuned, and please let us know that if you're having some doubts, use the discussion forum to raise those doubts, and we'll try to answer that. And I hope so far everything I have done is clear, but even if you have the slightest amount of doubt, please do not hesitate to use the discussion forum. Okay, so I'll stop the session now. Thank you for joining and attending, and we'll See you tomorrow. I mean, next week. Thank you.